All right, hello everyone. Welcome back to the hottest seminar. Today we have Niels van der Weide who will tell us about the internal languages of univalent categories.
Thank you for introducing me. Thank you for having me here. And good morning, afternoon, evening, night, or whatever it is for you to all of the audience. And indeed, I'll be talking today about the internal languages of univalent categories. So let me start with some kind of pictorial overview of what I want to talk about. So basically, there's a very strong connection between, on the one hand, type theory, and on the other hand, category theory. So for instance, if we're working with extensional type theory with sigma types, that's like kind of the internal language of categories with finite limits. We can use type theory to reason in a nice notation, which is also closer to what we're used to reason about these kind of categories. And we can extend our type theories to have more type formers and to have a more expressive language. For instance, we could also consider pi types, and that should be the internal language of locally Cartesian closed categories. Or we could consider a type of propositions, and then we are working with toposes. Or we could add like the type of natural numbers, and then we're looking at categories with natural numbers objects. And there are various ways to make this precise, and one very nice way to make this correspondence between type theory and category precise is some theorem that was proven by Clairambault and Dybjer. It was a correction of what was done by Seeley, but I'll be focusing on the work by Clairambault and Dybjer. What they showed is that on the one hand, we can form some kind of bicategory of models of theories. Of theories. So they represent these using categories with families with sufficient type formers. These type formers are sigma types and extensional identity types. And they need to add a requirement, what they call democracy, which relates context and types, which is going to be necessary, and I'll explain that more later. So on the one hand, you have these CWFs, and on the other hand, you have categories with finite limits. So this bicategory of categories with finite limits. And what they showed is that these two are biequivalent, meaning that basically they are the same thing. So they're equivalent. And they also extend this to the case of pi types and locally Cartesian closed categories on the other hand. And this is one way to make this correspondence between category theory and type theory very precise. So this is a nice theorem, and you can see it as like a foundational result that allows us to use type theory to reason about categories and to use categories as models of type theories. And one interesting aspect of this is the weakness. It is a biequivalence and not an equivalence of categories. And why is this so? Well, there's a nice sentence in their paper where they say, so we can ask whether Martin-Löf type theory with extensional identity types, sigma types, and pi types is an internal language for LCCCs. And we can answer yes, it is an internal language up to isomorphism. Because when you model type theory in a category with finite limits, there are small differences present. Because in a category, stuff holds up to isomorphism. When, for instance, we're going to show that a pullback along an identity gives you the same thing back, you only get it up to isomorphism, or you must choose your pullbacks really well. And in general, for category, stuff holds up to isomorphism. Well, if we do type theory, we always want to have equality. So if we do some substitution, we replace every variable by itself, then we should get the same thing back. And this would only be an isomorphism in category theory. And in order to deal with this, you actually need to take your model and you need to replace it with something equivalent in order to guarantee that all of the rules of type theory are modeled. So one thing that I think is quite interesting about this up to isomorphism is that I've been indoctrinated with univalent categories for a long time by now. And when I see this kind of thing, I for me, this is some kind of opportunity for univalent categories, because this might be a place where univalent categories are conceptually satisfying and where the usage of univalence could simplify our development. So let me first briefly recall what a univalent category is. So we say that a category is univalent if identity of objects, so when two objects are equal, is the same as isomorphism of objects. We can make this precise by saying that we have a map sending identities of objects to isomorphisms, and by saying that this map is an equivalence. And what is nice about univalent categories is two aspects. So first of all, we truly view objects up to isomorphism. So if two objects are equal, or if two objects are isomorphic, then they must have the same properties. And the second thing is that univalent categories themselves are viewed up to adjoint equivalence. So if we have two univalent categories that are adjoint equivalent, then we can transport all properties and structure from one to the other. So if we're working univalently, and if two objects are isomorphic, then they have the same properties. And if two categories are equivalent, then they have the same properties. And this is something that is quite nice, because it allows us to transport structure and properties along adjoint equivalences for free. And yes. So the theorem that I was interested in, and which will be the main topic of the talk now, is an analog of Dybjer's and Clairambault's theorem, but then for univalent categories. Let's make it more precise. So I take that theorem and I make several modifications. First, I add some adjectives. On the one hand, I require both of these bicategories to only involve univalent ones. So I look at univalent categories with finite limits, and I look at some kind of univalent notion of model. And the second deviation, this is where I truly deviate from Dybjer's or Clairambault's and Dybjer's development, is that rather than using categories with families, I use comprehension categories. I will explain later why, but this is also one deviation from their theorem. And then finally, I make a minor change to the typeformers, although this is equivalent. So it basically is essentially the same as working with extensional type theory, but it was a bit simpler for the proof. And then finally, I also looked at whether at extensions of this theorem to various classes of toposes, like pretoposes with the natural numbers object, with pi types, elementary toposes, and elementary toposes with the natural numbers. So the main theorem that we shall be looking at today is this theorem. And if you find it interesting, so first there's our whole formalization. And if you can click the link, you can click it and check it out. And then there also is a preprint, which is mentioned in the abstract as well. So if you want to read more about it, the preprint is where you can read it. So let me specify a bit more precise what I want to discuss today. So I'll start by arguing why I think comprehension categories are more suitable for interpreting dependent type theory than categories with families in univalent foundations. And I'll argue what kind of models are suitable for in this kind of setting. After that, I'll have a brief recap of typeformers in comprehension categories, the notion of democracy, and the bicategory of comprehension categories, which is one of the main things that we need to formulate this theorem. After that, I'll briefly recall the proof by Dybjer and Clairambault, although phrased in the language of comprehension categories, and because it's actually a very nice proof and it's quite beautiful, and I hope to make its beauty shine during this talk. And then finally, I'll discuss this extensions of this theorem and how we can modularly deal with this in a proof assistant. And whenever I have a chance, I will be discussing how Univalent helps us with the development and how it makes certain things simpler. So this is what I want to discuss today. This is the table of contents, and this is where we are because we just had the introduction. So let me start by arguing why I think comprehension categories are more suitable. And to do so, let me start by recalling categories with families. Because if you have been working on type theory recently, then all people would use this notion because it's quite convenient, it's quite intuitive, and it's very easy to explain and understand. While comprehension categories have been getting less attention because they are more difficult to understand and more disconnected from the syntax. So what is a category with families? Well, there are two main ingredients. The first one being a category of which the objects denote the context and of which the morphisms are context morphisms. The second ingredient is a functor that sends from this category C to families. What this means is that for every object C, I have a set of types in that context gamma. For every object gamma in C, I have a set of types in that context. And I also have a family of terms indexed by this type, by this collection of types. So here we have the collections of terms in type gamma, terms in context gamma of a given type. We also need to talk about context extension, but that's not super relevant for this talk. So if you want to read it, you can read it. If you don't want to read it, fine with me too. So this is a nice notion. But let's say we're going to study this in Univalent foundations, then there will basically be one thing that will really bother us. And that is this set. Why is this something that makes life hard? Well, let's say that our goal is to construct a CWF that represents the set model of a type theory. So what would this look like? Well, in that model, context should be sets and morphisms between context should be functions. All fine here. But when we're going to look at types, what we want is that types in a certain context are equivalent to families of sets indexed by this context. And that is problematic because if we're working in Univalent foundations, the type of sets does not form a set itself. So this thing is not a set. So if our types are equivalent to this, we're not going to have a set, and we can't model this with a CWF because then we're required to have a set of types in every context. And that is blocked by the fact that the type of sets has a more interesting identity type given by isomorphisms. So this is using CWFs is for that reason more suitable if you work in a setting with like uniqueness of identity proof, because if you are in a setting with UIP, then this is not an issue because you just have a set and completely fine. But if you want to work with H sets and with univalence, then this will block you from having a CWF. And this holds also more generally for univalent categories, because in a univalent category, the identity type of objects is the same as isomorphism. And objects could be isomorphic in different ways. And thus, a univalent category does not necessarily have a set of objects. So, if we start with some univalent category with finite limits, we do not have a nice CWF that is as follows, where the objects are objects, or where the contexts are objects in C, and where types in the context are equivalent to morphisms from some object to gamma. And this is again because in general we only have a one type of objects in a univalent category and not a set. So this CWF is something that we do not have. And the whole underlying reason for this is because this notion of model is based on discreteness. So one could formulate this in terms of discrete vibrations or equivalently presheaves. And if we're working in such a model that is based on discrete vibrations or presheaves, then our types are forced to form a set. And many different kinds of notions of models for type theory are discrete. For instance, categories with attributes, where discrete vibration is literally in the definition. Categories with families, that's with families, so with sets and a family on it, so presheaf based. And natural models, which also are based on presheaf. So if we use one of these kind of categorical structures to represent models of dependent type theory, then we are blocked by this set assumption, and that would prevent us from making a model from a univalent category. Instead, I would like to look at models that allow for more possibilities. So I would like to reject the discreteness assumption and instead work with more higher categorical structure. For instance, if we build our notion of model around the notion of vibration, then we have more flexibility in what our types are allowed to be. This is because vibrations are equivalent to pseudo-functors into categories. And if we make everything univalent, we're then permitted to have a one type of types in every context. And that gives us more, and that is basically what would allow us to have the desired models, because we got rid of this assumption that types must form a set. And we increased it a bit. They are of a higher age level now, but that's not an issue. And there are various notions of models that are built around vibrations. So for instance, the one that I shall be using, comprehension category, where you literally say, oh, we have a vibration. Then there's the notion of judgmental theories in this paper by Greta and Ivan, and generalized CWFs in this other paper by Greta and Jacopo. And this is more of a notion of natural model, but then phrased using arbitrary vibrations rather than discrete vibrations. So this is also a suitable notion of model. And then there has been current research in making a non-discrete version of CWFs, which is called coherent CWF. That, yeah, if you're interested in it, you can check out this types talk about it. So instead of using a notion of model of type theory that's based around discrete vibration, it is more suitable to use one that is based around a general notion of vibration that does not force you to have sets of types. So this is the kind of notion of model that I shall be using. Another important thing to remark is about splitness. So when we are looking at models of type theory, we always want to say, oh, if we take a substitution with identity, it must be equal to the original thing, and some similar thing for a substitution with a composition. It must be equal to whatever. If we're working with categories, then these kind of laws always hold up to isomorphism rather than equality. And because we're working univalently, such isomorphisms give rise to an identity, and thus, by working univalently, we don't need to worry too much about the splitness, because the required equalities still hold, because they hold as an isomorphism. There are also other kind of approaches. So in my approach, so what I'm doing is more focused on making models built around a set or univalent categories. And that is one approach. But one could also take an approach that accepts using discrete models, but modifies this notion of sets. So there's work by Daniel, Håkon, Anders, and Elisabeth on a category of iterative sets, and they show that it gives rise to a CWF. And what they essentially do is they take a different notion of set, and they show that you can get a CWF using this different notion of set. So there are also alternative routes possible in order to deal with this problem of not having a CWF of sets by, for instance, modifying the notion of set to iterative set. But our focus in this talk is on different kind of models, namely those arising from univalent categories. So this is more of an orthogonal approach to what we do. So because vibrations play an important role in my talk, in the sense that it's the basic thing of model, or basic notion that's needed for comprehension categories. And because I'll be talking about displayed categories and displayed bicategories later, I would like to recall how one defines vibrations in univalent foundations, because that is actually quite ingenious trick. So rather than using, normally in mathematics you say like a functor is a vibration if we can find suitable Cartesian lifts. But to phrase it, then either you need to use an isomorphism of objects and get something that's a bit weaker than you might want to have, or you need to talk about equality of objects, which is also not really what you want to do. But if you use a different approach where instead of talk about a P such that Px is blah, 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 you talk about objects over X, you can phrase this much nicer. And this is this notion of displayed category. It basically gives us a representation of a functor into a category C, but rather than phrasing it in terms of like functions, we phrase it in terms of like, what are the fibers? So what are the fibers of my objects and what are the fibers of my morphisms? So what is this notion? Well, for every X, so for every object X in C, we have a type of objects over X. So these are mapped to X. And for every morphism in my category, and if we have two more objects over the over domain and codomain of that morphism, we have a set of morphisms lying over that morphism. So these are the ones that are mapped to this given F. And we can basically phrase the notion of vibration almost verbatim using displayed categories, and that gives us a nice way to represent vibrations in a proof assistant and in univalent foundations. And displayed categories have also found many other applications, ranging from like modular constructions of categories and other things. So this is an important notion. So besides displayed categories, we can also formulate other gadgets from category theory in this displayed fashion. So for instance, we could formulate the notion of displayed functor, which is a functor lying over some functor between two categories, and then this displayed one is between two displayed categories. And we can formulate a notion of displayed natural transformation between two displayed functors. So each of these notions from category theory has a displayed analog. But I won't be discussing them in detail. Instead, I would like to recall how one defines comprehension categories in univalent foundations. And basically it is as follows. So I restrict myself to univalent categories because that's what I do. And also I restrict myself to full comprehension categories, which I shall explain soon. So what does a comprehension category consist of? Well, basically you should see it as this triangle. So first we have a category C with a terminal object. This category C represents context plus context morphisms, and the terminal object is the empty context. Second, we have a vibration D over C. This one represents types in a context, and that's what this D does. And then we also need to talk about context extension, so the comprehension, which we represent as a displayed functor from D to the arrow category. So what do we require for this functor chi? Well, we require that it preserves Cartesian morphisms, which is what we need to interpret substitution for terms correctly. And we require that it is fully faithful, which is this fullness requirement. So this is a notion of model for type theory that I used for the whole development. And this is how you should imagine it with this picture. And if we're then going to look at the set model, then we can just make it. So we can just take D to be the arrow category of sets, an identity functor, and yeah, we have this comprehension category. There's no H-level assumption blocking this thing from existing. So this is why I think the notion of comprehension category is more suitable if you want to study the languages of of univalent categories. So, are there any questions up to now, or I'll check the chat?
Nothing in chat.
Okay.
I guess I'll just add, so on the previous slides, when you're talking about the arrow categories, they're displayed over the codomains, right?
Yes. So indeed, for a comprehension category, you must display the arrow category via the codomain functor, because a comprehension category is like with this one being the codomain.
Yeah.
Thank you.
And oh, okay, never mind. Good.
Yes. Okay. So let's continue. So we must also talk about what is the bicategory of comprehension categories that we're interested in, and we must say how to interpret the type formers. And if we go back to Clairambault and Dybjer, what do they want? They want extensional identity types, and they want dependent sums for which the eta rule holds. They also assume democracy, which I will make explicit after 2 slides. And I actually used a bit simplified so that I didn't have to make any derivation. I also say, oh, I want unit types, binary product types, and equalizers, which was mainly to simplify the development. But how do we interpret this using comprehension categories? So binary product types, we're going to say, oh, D has fiber-wise binary products. So binary products in each fiber and preserved by substitution. Extensional identity types, well, usually it is with talking about left adjoints to contraction functors with a back-Shapely condition and a strongest assumption that gives us the reflection rule. I use fiber-wise equalizers instead because they are equivalent, and it was a bit simpler to use them because we need to derive equalizers. And yes, unit types. There I require fiber-wise terminal objects and that the comprehension functor preserves terminal objects. We need this requirement to connect terms or to connect functions in D to actual terms being sections of the projections. So if we assume fullness and this preserves terminal objects, then we can basically have only one obvious notion of term. So that's what we require for unit types. Then we have dependent sums, and then we follow the common slogan of quantifiers as adjoints. So dependent sums are left adjoints to weakening, and we need to have a back-Shapely condition to guarantee that they are preserved by substitution. But if we only require this, then we don't have enough, because we also want the eta rule. And to have the eta rule for dependent sums, we need to require an additional strongness assumption that says that these two types are isomorphic, or yeah, that's basically the additional assumption that we need in order to interpret sigma types correctly. And then there's this notion of democracy. The easiest way to understand and to remember it, and this is something that has been in my mind for many years, every context has a representative. So what does democracy say? If we have an object in C, then there's a type which represents this context, a type A in the empty context, such that gamma is isomorphic to this extension empty.a. So if we think of a context as something like x1 of type A1, x2 of type A2, blah, 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 xn of type AN, then this democracy is basically like this big sigma type of sigma x1, A1, x2, A2, blah, 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 AN. And that is democracy. And this gives us a connection between types and contexts, which is what we need for the biequivalence. And this leads to the main notion of comprehension category that I shall be using, which I call a democratic finite limit comprehension category, which is too much to say. So I call it DFL comprehension category. And what that is a democratic univalent full comprehension category with unit types, binary product types, equalizer types, and dependent sums. Unit types are redundant because they follow from democracy, but I kept them in. Binary product types are redundant because they follow from dependent sums. So these two are redundant, but I kept them in for simplicity. And equalizer types are equivalent to extensional identity types. So in this sense, it reflects what Clairambault and Dybjer did. Then there's always a question of what are the morphisms? So if we look at comprehension categories, we always have these triangles of like C, D, and arrow. So what are going to be the morphisms? Well, first we need a functor from C1 to C2. So we need a functor on the level of context. Then we need to have a functor over this functor, which is on the level of types. So that is a functor f and a displayed functor f bar. And then we need to say, how does it interact with context extension? Well, we say that it preserves context extension up to isomorphism. And that entails to saying that this triangle, or this square, I don't think these things squares and triangles, this square commutes up to natural isomorphism. And that says how it interacts with a context extension. And then we must also say that the type formers are preserved. So f bar preserves pairwise terminal object, binary products, and equalizers. And that's it. Note, we do not need to add an assumption about preservation of sigma types. That is because of the strongness assumption saying that the sigma types can be written with like gamma AB, though that follows from this. And we also don't need to require that democracy is preserved. This is a requirement in Clairambault and Dybjer, but you can actually derive it in general. So this is a requirement that I also don't add. And then we can define this bicategory. So the objects are the things that I mentioned before. So comprehension categories with all of these requirements. Morphisms are the morphisms that are defined on the previous slide. And for the two cells, yeah, if you want to know, you can ask. There is a bit more notation. So the two cells I will leave to your imagination or for the Q&A. And one can show that this gives rise to a univalent bicategory, meaning that such comprehension categories are identified up to adjoint equivalence. So if two comprehension categories are adjoint equivalent, then they have the same properties. So now let's look at the first theorem of interest, saying that the bicategory of categories with finite limits, univalent categories with finite limits, and the thing that I just discussed, that they are biequivalent. And this was the first theorem by Clairambault and Dybjer. So a brief recap of what this one is. Objects are categories with finite limits. One cells are functors that preserve finite limits. And the two cells are natural transformations. So if we want to prove this, how are we going to do it? We need to make two pseudo-functors and two pseudo-transformations. We need to give a map from categories to comprehension categories. So since every category to like its theory or so, and then also the other way around. And we need to have pseudo-transformations that connect the compositions to the identity. So those are going to be like going back and forth is the same as identity. And usually when people construct biequivalences, they need to also show that these are adjoint equivalences. And then they construct a pseudo-transformation in the other direction to invertible modification about doing whatever. But that's actually not really needed because it suffices to show that they are pointwise adjoint equivalences. And that simplifies the whole thing because I only need to make one pseudo-transformation like this and one like this, done. I don't need to make them in the other way around. No need to worry about invertible modification. It's just this and this check that they are pointwise adjoint equivalences. So the proof that I do kind of follows what Dybjer and Clairambault did, but is slightly rephrased. So first, how do we go from a category to a model of type theory? Okay, we have a C, which is a univalent category with finite limits. And then we can form this comprehension category that we might recognize from the set model. So we take the arrow category, identity, over this. This is a comprehension category. We can show that it models all the necessary type formers. That's a matter of doing work. We can show that it's univalent because the arrow category is univalent and we assume C to be univalent. So check. So this is fine. And if one has a lot of willpower, then they can also show that this is a pseudo-functorial action, meaning that it also acts well on the morphisms, on the two cells, and whatever. In that part, nothing really special happens. It's mainly approved by lots of willpower. So this is the first thing. And if you compare to what people do in set theory, then the main difference is that I'm not taking this splitting. So if you work set theoretically, then this arrow category is almost the right thing. Not completely, but almost, because substitution is not interpreted correctly in the arrow category. And for that reason, we must replace it by something equivalent, where the vibration is actually split and correctly models all the rules regarding substitution. So if one would be working in set theory and still want to do this development with comprehension categories, then this is basically what the construction would look like. Okay, other way around. So let's say we have a comprehension category, and now we need to go to a category with finite limits. So we have this whole thing, and this gives rise to a category C. So we sent it to the category of context. The thing that we really need to do, and where the challenge lies, is in verifying that C is finitely complete. And for that, we have the following key lemma. So if we have a comprehension category like this, then this functor, also we assume all the type forms that I mentioned before, so democracy, sigma, whatever, and whatever. If we have a comprehension category like that, then this functor chi is essentially surjective. Since we assumed our comprehension category to be full, chi is an equivalence, and thus D and the arrow category are equivalent as categories. So we can transport structure from D, of which we assumed a lot, to the arrow category and deduce stuff about the arrow category. In particular, we can deduce information about the fibers. So by assumption, every fiber dx is has equalizers and whatever products terminal. And thus this is also the case for every fiber of the arrow category. And thus in particular for C, because that is the fiber of the terminal object. So because D is then finally complete, we also know for C. So here, what we're doing is transporting stuff along equivalences, which is what univalence makes very nice. So now we need to make the unit and co-unit. One of them is not that special because we start with a univalent category, make this comprehension category with the arrows, and then we take the category of context. Oh, we got the same thing back. Oh, we can take the identity, pointwise adjoint equivalence, yay. Also special. But if we go the other way around, so we start with the comprehension category and we go to the category of context and then back with an arrow, then we need to show that this thing is equivalent to this one. So what we need to do is we need to make an adjoint equivalence like this. And for that, we use the key lemma that I just mentioned, where it says that this chi is an adjoint equivalence. And with this in place, you can make this morphism, and then you can say, oh, this is an adjoint equivalence, and everything is okay. And this basically is this whole proof. For this basically is what this biequivalence entails to. These are the main steps. And there are several points where I make use of the fact that we're working univalently. For instance, we were talking about the interpretation of substitution, where I did not use a splitting. So I just used the arrow category rather than some kind of a split replacement of it. Because if we're working univalently, if stuff holds up to, if two things are isomorphic, then they're equal, no need for the splitting. Second, and this will be used a lot actually also in extensions, if we often need to transfer stuff around, along adjoint equivalences. For instance, two categories might be both, we know that C is finally complete and some C prime is equivalent to it. Then we want to show that C prime also is finally complete. And this is completely free if we work univalently. And then there's another aspect that I haven't highlighted that much throughout the proof just now, but I did use implicitly, is that we want to characterize what adjoint equivalences are. For instance, we want to characterize that adjoint equivalence between pseudo-functors are pseudo-transformations that are pointwise adjoint equivalences. We want to say that adjoint equivalences of comprehension categories are given by an adjoint equivalence between their categories of context and an adjoint equivalence over it between their displayed categories of types. And these kind of statements also help simplifying the development. And in their proof, I actually make use of univalence. How? So let's focus on this theorem. So a pseudo-transformation is an adjoint equivalence in the bicategory of pseudo-functors if it is a pointwise adjoint equivalence. So if you check the literature, I think the only thing where it got proven was in Johnson and Yao, where they used mate calculus. But if we use univalence, then we can get, in my opinion, a nicer proof, and that basically entails to two tricks: using displayed bicategories and using equivalence induction. And the idea being is that we can build a category of pseudo-functors as a chain of displayed bicategories. We start with almost pseudo-functors, like they only have a map on objects. Then we add an action on one cell, action on two cell, identity and whatever, the loss. And then for each of these layers, we say, oh, actually this reflects adjoint equivalences. And then what happens is that it simplifies the mate calculus you have to do. Because if we work only with maps on objects, it's not that hard to verify that adjoint equivalences are determined pointwise. And then by reflecting it all the time, we can deduce that it's the same for the bicategory of pseudo-functors. So in that sense, we use these two things. Let me make it a bit more precise. If you have any more questions about the details of proof, I can show after the talk. So first thing, we have this notion of displayed bicategory. It is similar to a displayed category, but 2 versus 1. Instead of working one-dimensional, we become two-dimensional. So we have objects over objects in the base, one cells over one cells in the base, two cells over two cells in the base, so two-dimensional. And there's much more, because bicategories are very big things with many operations, and luckily I didn't say this all on the slide. If this is something you want to know, the literature exists for a reason. So that is where to check it. And one example of a displayed bicategory is given by the bicategory of vibrations. So let's say we start with the bicategory of univalent categories, and we define a displayed bicategory over it. Objects over some category are vibrations on that category. One cells are Cartesian functors, and two cells are given by natural transformations. And can give many more examples, and that is basically what we have, what you can, a lot of bicategories can be constructed with like a chain of displayed bicategories. And the main step is that if we want to characterize adjoint equivalence, one thing you often want to do is show some kind of, this thing reflects adjoint equivalences. So we have a bicategory B2 with objects with a lot of structure, B1 with objects with less structure, and then this P forgets some of the structure. And then in B1, it is easy to characterize the adjoint equivalences by hand. And then by showing that P reflects adjoint equivalences, you know what they are in B2. However, if we phrase this by pseudo-functors, then it doesn't help that much because we just have this. But if we phrase this using displayed bicategories, then suddenly it becomes easier. Why? Because we're saying, oh, we have this arbitrary adjoint equivalence in the base and something over it. And what univalence allows us to do is doing induction on this adjoint equivalence. So if we want to show for all x, for all y, for all adjoint equivalences from x to y, something holds, univalence allows us to restrict to the case that this E is identity. And that is also what simplifies calculations, because of course the identity is going to be much easier than the arbitrary adjoint equivalence. So now using in univalence this way, we can simplify characterizations of what adjoint equivalences are, and yeah, that's also one place where it is used in the proof. So, final part of the talk, how do we extend this theorem to toposes? And here I won't be discussing many details, but more like what are the main techniques being used here. So let's say our goal is to extend this bicategory to involve more type formers and more categorical structure. The first thing, and this was also done by Clairambault and Dybjer, is pi types. So then we look at comprehension categories with all the stuff that I've mentioned so far. And then you also look at pi types, which are right adjoint to weakening, satisfying back-Chevrolet. And we look at locally Cartesian closed categories rather than categories with finite limits. If you look at how this biequivalence is defined, in this case, then in essence, it takes the one between finite limit categories and comprehension categories, and it extends it to also include pi types and locally Cartesian closeness. So in essence, what you're doing is you're extending a given biequivalence to incorporate more structure. Normally, if we do this on pen and paper, we are like, we already did this and we keep this informal and we don't really make the modularity very precise. But if we make use of the whole displayed machinery, then we can make this actually quite precise. Why? Well, we can see the bicategory of LCCCs and the other one as a total bicategory of some displayed category or displayed bicategory. And how do we make the total? Well, pairing something in the base, something over it. For the 0 cells, 1 cells, and the 2 cells, we take something in the base and something over it, pair it, total bicategory. So if we think of B as objects and D as additional structure or properties, then we're extending things in B with additional structure that we defined. And the relevant examples, we can define LCCC as the total bicategory of the displayed bicategory of over finite limits that says that C is locally Cartesian closed, so right adjoints to pullback. And similarly for comprehension categories with pi types, we just say, oh, pi types, yay. So, and we can define many the kind of display gadgets. We can define displayed bicategories, displayed pseudo-functors, displayed pseudo-transformation, displayed invertible modifications, and displayed biequivalences. All of them we can basically define. And luckily for you, you don't have to see the definition because that would completely fill the slide, and so be it. So if you want to check what they are, the literature exists for a reason. And the notion that we're interested in is this notion of displayed bicategory that allows us to extend a biequivalence to total bicategories of two displayed bicategories. So the main idea of extending this biequivalence to pi types is not so much by just redoing the proof and doing it again, but it is to use displayed biequivalence to also prevent this reusage. On a pen and paper, you might not really care that much. You just say, oh, we know this. But if you do this in a proof assistant, then this is something you care about because you don't want to type it all over again because it doesn't believe in your, oh, we can do it again. And yeah. So to extend this biequivalence to take more type formers into account, display biequivalences are our main tool. And this is all done in Dybjer, Clairambault. So they extended, they looked at finite limit and LCCC, but we can also look at more kind of extensions. And that includes more kind of type formers. What is the main idea here? Let's say we want to interpret disjoint sums in a comprehension category. How are we going to do that? Every fiber has disjoint sum, so the fibers are extensive and substitution preserves coproducts. Okay, what about quotient types? The fibers are exact and substitution preserves regular epis. Okay, what about subobject classifiers? Every fiber has a subobject classifier and substitution preserves subobject classifiers. So each of these type forms is basically interpreted in the same kind of way. And this is something that is not invented by me. This is actually, I learned from this paper with a long title, Modular Correspondences Between Dependent Type Theories and Categories Including Pretopos and Topoi by Maietti, which is this notion of a local property. So what is a local property? On this slide, I've reformulated to univalent categories because that fits the idea of the talk. So first, we have some kind of property on categories with finite limits. For instance, having a subobject classifier or being exact or whatever. Then we have a property on functors. This is like preservation. So for instance, if we would look at like the property on categories being extensive, you would say preserves coproduct. If we would look at the property on categories being exact, then here we would say preserves regular epis. So we have two of these properties, one on categories, one on functors. What do we require? First of all, that this property is closed under slicing. That is because when we interpret these type formers in a category with this property, we always need to put it in the slices. I forgot the substitution requirement, but we need to have identity and composition is satisfy this property. Substitution as well, although that's not on the slide. But there's one more thing that I need, namely that it is suitably functorial. So if we have a functor that preserves finite limits and that have this property, then it also holds for every fiber functor going from C1x to C2 over Fx. This is not a requirement in the work by Maietti because Maietti is only interested in soundness and completeness. So there's no need to really look at the morphisms like this. But because I look at biequivalences and then you need to take the morphisms into account, I need to require this. So this is the notion of local property that I use. And there are many examples. So being exact, which represents quotient types, extensive, which represents disjoint sum types, pretoposes, which is the conjunction of these two, so some kind of universe for predicative mathematics, having a subobject classifier, which gives us in predicative universe of propositions, and having a parameterized natural numbers object, which gives us the type of natural numbers. And all of these are examples of local properties. And then we can extend the biequivalence to also incorporate local properties. What does this look like? So for the side of categories with finite limits, we say that it satisfies this property. And on the side of comprehension categories, we say every fiber satisfies this property, and the substitution functor satisfies the property for functors. And this immediately allows us to instantiate this for exactness, extensiveness, and so on. And by combining it with pi types, we can then conclude what the internal languages of various classes of toposes is. And yeah, then yeah, that basically incorporates a local property and possibly pi types, because these two don't have pi types. But for these three, we incorporate a local property and the pi types, and then we can extend this theorem to various classes of toposes by connecting these two IDs. So that's the main content of the talk. So what did we do? Analog of Clairambault and Dybjer for univalent categories. So they gave an internal language theory for univalent category for ordinary categories in set theory, and we studied it in univalent foundations for univalent categories. And one of the first observations is that it is necessary to use models of type theory that are not discrete by nature. For instance, comprehension categories or generalized categories with families, instead of something like natural models or categories with families. So that was the first observation. And another observation is that univalence helps us to simplify certain aspects of the proof, because at many places we need to transport structure or properties along adjoint equivalences. And this is something we also need in the extensions. So we need, if C is locally Cartesian closed, then C prime is also locally Cartesian closed if we have an adjoint equivalence between C and C prime. These kind of statements are things that we use, that are regularly needed. So that those become very simple if we assume univalence. It also helps us to characterize what adjoint equivalents in certain bicategories are, and it removes the necessity of splitting. The other thing in the that is a main thing of this talk, or a main thing to remember, is that you can extend this theorem by Clairambault and Dybjer by mainly following the work of Maietti with modification to require factoriality in a suitable way. And from this, to really make these extensions modular, the main tool is displayed biequivalences. And there are many ways to look further. So first, what is a suitable syntax? That is something I haven't thought about. So I've been looking more at notions of models rather than what is the actual syntax. And this is something that will be interesting, and also reasoning about the syntax. And second, I've been constantly looking at extensional type theory, which might be kind of weird at the Homotopy type theory seminar, because we do intensional type theory. So how could one make these kind of internal language theorems for intensional type theory? And there has been recent work on this by Daniel Otten and Matteus Badetto. And this is the thing that I could find. And they compared path categories and comprehension categories. So let me finish this talk by slightly modifying what Clairambault and Dybjer say. So we can ask whether Martin-Löf type theory with extensional identity types, sigma and pi types, is an internal language for univalent LCCCs. And we can answer yes, just yes. No need for up to isomorphism. We can answer the analogous question in the same way for pretoposes, pi pretoposes, elementary toposes, and elementary toposes with natural numbers objects. So if anyone wants to read further, this is the relevant preprint, and now it's time for some questions.
Great. Well, thank you very much. Let's all silently applaud, or use the applauding reaction.
Mm-hmm.
Okay, well, if anyone has a question, feel free to unmute and ask. I guess, okay, so Ali has a question in chat saying, just to check, you're using univalence as a bookkeeping tool rather than something necessary for the proof. If you had the will, you'd be able to do all the proofs without it, right?
Yes. Yeah, so so if you look at like univalent foundation, you can basically do category theory in two ways. Either univalently and you study everything up to adjoint equivalence, or you can use strict categories where you study them up to isomorphism. So I have been not very faithful to the development by Clairambault and Dybjer because I use this notion of univalent category. But if you want to stay more faithful to it, you can use strict categories and basically redevelop their proof without univalence. It is thus not necessary to assume it if you want to have some analog for this theorem, because you can basically study it in two ways, either univalently or strictly. And yes. So it's indeed not necessary, but I do think there are several aspects to it that make it nicer, I think.
I guess I'll follow on to that with a question of my own, which is, I feel like maybe, so you've, by switching to, comprehension categories, and I think you had very good reasons, but you're kind of moving the strict thing closer to the weak thing, right? In terms of the biequivalence being between things that behave differently. Right, so like you no longer need to worry about replacing fibration with a split one or something like that. Do you think anything is kind of lost in terms of the content of the theorem here by making those changes?
I think the main thing that really is, I would say open question rather than lost, because lost implies for sure, while I think this is more of an open question, and that lies more on the syntactical development, because when we treat the syntax of type theory, we always think of it very strictly. Everything is a set, we don't require any coherences, it's just how it is. But in this univalent development, we also have to treat the syntax differently. So our syntax will have coherences in it, because we don't assume stuff to be a set, and we might have multiple ways to prove two types are equal. So in that sense, the original or the usual treatment of syntax is lost, but it might be to develop syntax of type theory in a different way that will fit this univalent development. So as far as I know, this is like not a question that really has been answered, but one thing that's also changed, and I think that is basically answers your question, is the treatment of syntax becomes differently, because we can't use the usual treatment with everything strict. We must modify our treatment of syntax.
Yeah, that's a great point. Yeah, thanks. So I guess you've spun it into, that you need to do future research. Yeah, good.
Yes.
So Peter has his hand up. Can go ahead and ask.
Yeah, hi. So actually, it's a related question. You mentioned these generalized CWFs by Corallia, Emenegger, Diliberti, right?
Yes.
So would the theorem be true if you instead said you have a bicategory of univalent generalized CWFs?
Mm-hmm.
Would that be biequivalent to the univalent, finite limit categories, for example,
Yes.
provided you have the extra structure?
Yes. So this paper by Greta and by Jacopo is showing that the bicategory of comprehension categories is biequivalent to that of the generalized CWFs. So generalized CWFs is also a perfectly fine replacement. So
right. So it really is a theorem.
Yes. So here, the only reason why I prefer comprehension categories over generalized CWFs is because comprehension categories put emphasis or put priority or put on the foreground this comprehension functor, which is also important in the proof, because is very much about saying that this chi is an adjoint equivalence. But you could perfectly do this with generalized CWFs as well. So there are going to be other different options as well. So the main requirement that I have is non-discreteness, and this is not unique to comprehension categories.
Right, so a follow-up question then is, I mean, it probably follows from what you have already said, but what goes wrong if you try to build a bicategory of univalent categories with families in the original sense? I mean, being closer to what we were in, our paper with Pierre. Is it not even a univalent bicategory?
So CWS, if you require the C to be univalent, you get a nice univalent bicategory. So CWS will form a univalent bicategory. But the thing that, and that's the thing that I think will go wrong, is when you would go for from categories to CWF, you somehow need to pick the collection of types. And that is something that doesn't have a clear path, because you want the types to be equivalent to this, but it is suddenly required to be a set, which is not possible in a univalent category. So CWS will still form a univalent bicategory, and something you can perfectly show, but the problem lies more on this construction to go from categories to CWS, because the objects do not form a set in general.
Okay, yeah, thank you.
Thank you.
Any other questions?
This is there's a chat. There's
Yeah.
a question in the chat. So this isn't a problem if extensional type theory. So I interpret this as this problem, which is indeed the case. So if you work in a setting where you have UIP, then there's no problem with going from a category to a CWF, because the objects will form a set. So this will then be a perfectly valid way of doing it. And this is also the reason why in the paper by Peter and Pierre, why they could do it with CWFs, because they're working in set theoretic foundations. So there's no hindrance of the age levels being incorrect or not fitting.
Right.
So yeah, so this is more of a foundational aspect to it, because the univalence will increase some age levels, and then you need to incorporate that in your mathematical development.
I guess I'll ask another question. So this local property thing you talked about at the end was very cool. Could you modularize the proof downward, where, so what I mean is instead of starting from the assumption that you have, you know, finite limits and that you could start with some weaker structure where you only have some pullbacks, and then you introduce, you know, unit and pi and sigma as some sort of structure that you have sort of in each slice that is preserved between the slices.
So this is an interesting approach, and if you look at like the code, there's certain aspects to it. So when we look at the way the displayed bicategories are defined, is, for instance, we define the comprehension category, and then on top of that is unit, equalize, and so on. So they are defined on top of there. But I think the part where stuff might go wrong is the key lemma, which is, where's, oh, this one. So here, you do need certain aspects. You do need sigma types, and you do need extensional identity types to show that chi is essentially surjective. So the kind of starting point needs to be strong enough to guarantee that this chi is essentially surjective. Because if you don't start from that, then maybe there are still possibilities, but it's then at least not clear what it should be, I think.
Right. Yeah. I mean, I think it would be a major change to the proof, definitely. Yeah.
Yes.
That's fair. And is there a problem with pi? So I mean, that makes sense for a sigma inequality, but what about doing pi in that way?
So okay, so in principle, you could perfectly well do pi in with a local property, because being locally Cartesian closed is a local property. The reason why I separated pi is because for pi types, the way you normally would interpret that as comprehension categories is with quantifiers as adjoints. And if you would phrase pi as a local property, same thing, I guess, but you would not have at least directly the whole quantifier as adjoint story in it. So you would then need to derive the right adjoints for substitution. So pi is also a perfect local property, but I just chose to separate it because I want a quantifier as adjoints.
Sure. You want it to be closer to the categorical formulation. Yeah.
Indeed.
Great. Are there any other questions from anyone? Okay, well, I guess let's thank Niels once again.
Thank
Great
you
talk.
all for listening and attending.
And we'll see you in 2 weeks.
Thank you.